Hi, I'm Sabina Stanley, a planetary scientist at Johns Hopkins University. I'd like to share with you one implication from the famous Apollo moon rocks that is not so widely appreciated. It's an exciting story, a story in which the giant planets change their distance from the Sun. The story begins like this. 4 billion years ago, the inner solar system apparently experienced an unexpectedly large number of meteor collisions that scientists typically call the Late Heavy Bombardment. This was over 500 million years after the Sun and planets had formed. So the number of collisions should have been declining, not suddenly increasing. The evidence for a spike in the number of collisions came first and above all from the Apollo missions bringing back lunar samples for study on Earth. Many of these famous samples from the Moon were of rocks that had been deformed or created by melting during large impacts. These crystalline melt rocks could not have formed without large impacts, tens to hundreds of kilometers in extent. And here's what was surprising. The ages of those melt rocks all cluster between about 3.75 and 3.95 billion years ago. This suggested that several large impacts occurred on the Moon during a concentrated time period of 200 million years. Geologically, a short amount of time. Other lunar samples provided ages for some of the large impact basins we see on the near side, like the Imbrium, Nectaris, and Serenitatis basins. The ages of the large impact basins were somewhat more spread out, from about 4.2 billion to about 3.7 billion years old. So there's some uncertainty about how to describe the duration of bombardment. But the evidence seems strong that there were a lot more impacts and much larger impacts around this time, compared to earlier or later times. Some supporting evidence also comes from craters on Mercury and Mars, plus meteorites that have landed on Earth. But based primarily on moon rocks, the evidence points to a spike in the number of impacts around 4 billion years ago. Okay, so what could cause a sudden spike in the number of impactors traveling to the inner solar system and hitting our moon and other locations? We would normally expect a steady decline in the number of impactors over time. If there was a big increase in the number of impacts, then perhaps there was also a big but more temporary disturbance, something big that perturbed a much larger number of impactors inwards from the asteroid belt and Kuiper belt. If we want a big disturbance, the biggest planets, especially Jupiter, are the natural place to look. Computer simulations allow us to study how the giant planets formed and gravitationally interacted early in the solar system. These simulations demonstrate that the giant planets can migrate their orbits somewhat during their formation. This idea that giant planets like Jupiter and Saturn actually migrate was a huge surprise, but the idea makes more sense after studying thousands of exoplanets orbiting other stars. Sometimes, those gas giant planets migrate very close to their parent stars. In our own solar system, we don't really know what the original configuration of the giant planets was just after they formed. But we can run lots of simulations with different possibilities and see which ones eventually evolve into the system we see today. One model that does a very nice job is the so-called Nice model. Nice here refers to the city of Nice, France, because the model was initially developed by scientists at an astronomical observatory near Nice. So the Nice model begins with the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, situated more closely in space than they are today. Their orbits were more compact, fitting all 4 planets between about 5 and 17 times Earth's distance from the Sun. Compare that to today, where Jupiter resides at 5, but Saturn is at 9, Uranus at 19, and Neptune is all the way out at 30 times Earth's distance from the Sun. During this early time, a disk of icy planetesimals with a total mass of tens of Earth masses would have existed out beyond where the giant planets were forming. Out there, the orbital speeds were too slow and the material too sparse to form a giant planet. Every once in a while, an icy planetesimal from this disk would be perturbed into the region of the giant planets. But when one of these planetesimals is scattered inwards by a planet, the giant planet's orbit is pushed a bit outwards. Momentum must be conserved. It's similar to why pushing yourself off a skateboard in one direction means the skateboard goes in the other direction. So now picture one of these planetesimals first encountering Neptune on its way in, pushing Neptune outward a tiny bit, as the planetesimal moves inwards. Then the planetesimal gets to Uranus and scatters inwards even more, moving Uranus out a tiny bit. And the same thing happens yet again when the planetesimal encounters Saturn. Now, admittedly, these outward perturbations of the giant planets would be extremely small. And not every encounter would result in an inward scattering of the planetesimal. Other directions are still possible, but on average, the odds are better that the planetesimal gets scattered inwards when encountering Neptune, Uranus, and Saturn. And if successive planetesimals are getting scattered inward over and over again, then the combined effect can be to move the planet's orbits outwards. But something different happens when the inward scattered planetesimal finally reaches Jupiter. Jupiter is so massive that Jupiter is more likely, on average, to fling the planetesimal into a highly elliptical orbit, taking the object further outward in the solar system. But every time a planetesimal is flung outwards, then Jupiter migrates inwards a bit. So Jupiter moves inwards, while Saturn, Uranus, and Neptune each move outwards. And all this continues to go on for some time, until Jupiter and Saturn end up in a very special configuration. As Jupiter is moving inwards, its orbital period is decreasing. As Saturn's orbit is moving outwards, its orbital period is increasing. Eventually, they reach a state where Jupiter completes exactly 2 whole orbits every time Saturn completes 1. They are now in a 2-to-1 orbit-orbit resonance. What this resonance means is that Jupiter and Saturn can gravitationally influence each other more and in a quite regular way. And what happens is they also perturb each other into orbits that are less circular and more elliptical. That means that Jupiter and Saturn cross through a larger range of orbital distances during their orbits. But taking the 2 biggest planets in the solar system and giving them orbits that are less circular and causing them to visit new places can cause all hell to break loose among all the remaining planetesimals in the solar system. Saturn quickly moves to a new position closer to where we find it today, out around 10 astronomical units, 10 times Earth's distance from the Sun. But if Saturn moves, then this has implications for Uranus and Neptune. Gravitational interactions with Saturn move Uranus and Neptune onto more elliptical orbits of their own, pushing them to cross farther out in the solar system. But as Uranus and Neptune migrated to orbits farther from the Sun, that destabilized the disk of small bodies out near Pluto. Some of those icy planetesimals, from what is called the Kuiper Belt, would be thrown into the inner solar system, producing a spike in bombardment of the inner planets. And about half the time when you run simulations with the Nice model, Neptune and Uranus switch places during their outward migration. In these versions of the model, Neptune was originally closer to the Sun than Uranus, the reverse of what we have today. This scenario is appealing because Neptune is almost 18% more massive than Uranus. For a given composition, we would have expected, all other things being equal, for Neptune, the more massive, to form closer to the Sun, where the protoplanetary disk was denser. Anyway, the end scenario is the giant planets, where we see them today, preceded by movement of the giant planets that caused increased bombardment in the early solar system. A lot depends on small details in the initial conditions of the models, but many possibilities lead to a major destabilization migration of the giant planets and flinging of planetesimals into the inner solar system. And there's even more, but this gives you an idea. I love how the Nice model opens our eyes to possibilities. The orbits of the giant planets dance around the solar system as the giants migrate, and the model is able to explain some previously taken for granted features we see in the solar system. But we don't know for sure that the model describes what actually happened. Even the late heavy bombardment, one of the major consequences that made the Nice model so attractive, may not be real. That's because there is some debate over evidence from the moon rocks supporting the claim that there was a spike in large impacts around 4 billion years ago. The debate stems from looking at the locations where we got our lunar samples during the Apollo missions. After all, It was these lunar samples that provided the first and strongest evidence that a late, heavy series of large impacts occurred in a relatively short geologic time. But it's possible that all of these moon rock samples are actually sampling from just one very large impact crater on the moon, Imbrium. That's not because we collected all the samples from a single location, but because the Imbrium impact would have spread ejecta over large distances surrounding the basin. And since Imbrium is the youngest of the large impact basins, the ejecta would have landed on top. Could it be possible that samples we collected from 6 different locations on the moon all happened to be ejecta from Imbrium? If so, that would explain, but a very different way, why all the ages in the samples cluster around the age of Imbrium. All those impacts still happened. It's just that they may not have happened so close together in time. Instead, it may be that there was a more steady and less dramatic flux of impactors from the beginning of the solar system, 4.5 billion years ago, down to about 3.5 billion years ago, without a spike centered at 4 billion years ago. And the fact that we don't see a lot of impact melt crystals older than about 4.2 billion years may be simply because older material was more likely to be pulverized by later impacts. Perhaps virtually all the older evidence has been destroyed. So which is it? Was there a concentrated bombardment caused by a dance of the giant planets, or not? Perhaps the most important thing that will help are more samples from the moon, from a wider variety of locations and different impact basins. After all, the ages of surface features on Mars, Mercury, and Venus are all anchored to ages of craters determined from lunar samples, combined with counting and comparing the relative number of craters on each world. If more samples from the moon resulted in a correction to the ages previously determined for lunar features, that would cause to revise the timing and sequence of events throughout the inner solar system. The timing of events early in the solar system may be fundamentally changed by better knowledge of lunar impact basins. Bringing samples back from the moon now seems so easy. We did it during the Apollo program, and yet no samples have been brought back to Earth from the moon since the mid-1970s. Naturally, scientists have lots of hopes and plans for new samples from the moon. The more samples, the better a picture we can develop about the timing of lunar impacts and the solar system as a whole. We need to return to the moon to sample from other locations on the moon that have no chance of containing the ejecta from the relatively young Imbrium basin. We need a bigger collection of moon rocks to tell us when and whether a concentrated period of late heavy bombardment even happened at all. And once we confirm or revise when and whether a big increase in impacts occurred, that will confirm whether the giant planets really did go dancing around the solar system, disrupting all the smaller bodies and causing a time with a huge increase in impact craters. In short, more moon rocks are going to tell us how the solar system formed.